This is 1.9 Acid Base Titrations. So, you should be able to demonstrate understanding of the concept of weak and strong acids and bases in terms of dissociation of hydrogen ions and hydroxide ions. Demonstrate understanding of the techniques and procedures used when experimentally carrying out acid-base titrations involving strong acid, strong base, strong acid, weak base, and weak acid, strong base. For example, determination of the degree of hydration in a sample of sodium carbonate and analysis of vinegar. You should be able to select the correct indicator for each type of titration and recall the colour changes of phenolphthalein and methyl orange at the end point. Identify uncertainties in measurements and calculate the uncertainty when two burette readings are used to calculate a titer value. Select appropriate titration data ignoring outliers in order to calculate mean titers. Calculate concentrations and volumes for titration calculations. Demonstrate knowledge of the term molarity, M, and the units of concentration, for example, moles per dm cubed and grams per dm cubed. And finally, describe the techniques and procedures used to prepare a standard solution of required concentration. So if we think first about solution concentration, a solution consists of a substance that is dissolved, that's the solute, and the substance that is doing the dissolving, which is the solvent. Solutions may be coloured or colourless, but they are always clear and never cloudy. So for solid substances, the chemical amount of the substance in moles can be calculated from the mass of the substance and its molar mass. However, most chemical reactions take place in solution. If we want to know the amount of substance in solution, then we must know the concentration of the solution and its volume. So the concentration of a solution is the number of moles or mass present in a stated volume. Concentration in chemistry can be expressed as the molar concentration, molarity, M, of a solution. Molarity is the concentration in moles per dm cubed expressed using capital M. So the formula here is moles equals the volume in cubic centimetres times the concentration, moles per dm cubed, over 1,000. If you want to rearrange that to get concentration is the number of moles times 1,000 over the volume, where the volume is the number of moles times 1,000 divided by the concentration. And remember, 1,000 cubic centimetres is 1 dm cubed, is 10 to the minus 3 metres cubed. So an example then, what's the concentration of a solution of 80 grams of sodium hydroxide and 4 dm cubed of solution? So we work out the formula mass of sodium hydroxide, which is 40. Number of moles is mass divided by the formula mass, so 80 divided by 40, which is 2 moles. The concentration then is the amount of solute in moles over the volume of solution, in dm cubed, which is 2 divided by 4, which is 0.5 moles per dm cubed. Volumetric analysis. Titration is a laboratory procedure where a measured volume of one solution of known concentration is added to a known volume of another reagent of unknown concentration until the reaction is complete. So the operation is an example of volumetric or titrometric analysis, and the end point is usually shown by the colour change of an indicator. The main pieces of apparatus used in a titration are a burette, a pipette with safety filler, a volumetric flask, and several conical flasks. Now, a standard solution is a solution for which the concentration is known. So to prepare a standard solution, a definite amount of solute must be dissolved in a definite volume of solvent to give a definite concentration of solution. The definite amount of material is measured by weighing, and the definite volume of solution prepared in a volumetric flask. So a volumetric flask contains a definite volume when correctly filled to the calibration mark. The procedure used to prepare a standard solution is summarised as follows. First, you weigh out an accurate mass of a solid in a beaker and dissolve a small amount of deionised water, stirring with a glass rod. You transfer the solution with rinsing to the volumetric flask. Next, you rinse the beaker and the glass rod with deionized water and add to the volumetric flask. You make it up to the mark by adding deionized water to the volumetric flask until the bottom of the meniscus is on the mark, and you stopper the flask, invert it to mix it thoroughly. Now, the procedure for a titration is, first of all, you rinse the burette with the solution you're going to fill it with. Then you fill the burette with this solution, which is usually the solution of known concentration, or the standard solution. Then, using a pipette filler, you rinse the pipette with the solution you're going to pipette into the conical flask. Then you pipette 25 cubic centimetres of this solution into 3 different conical flasks. You add 2 to 3 drops of a suitable indicator to each conical flask. Add the solution from the burette until the indicator just changes colour, and then you repeat the titration to achieve 2 or 3 concordant results, adding the solution dropwise near the end point. And you calculate the average titer from 2 accurate titer values. So safety during a titration involves the use of a pipette filler and the use of gloves when it's appropriate. Accuracy during the titration means you rinse the apparatus with the appropriate solution. You add the solution from the burette slowly or dropwise at the end point or colour change of the indicator. You swirl the flask and wash down the sides of the flask with distilled or deionized water. And you read the burette at the bottom of the meniscus. Reliability during a titration means you repeat the titration 2 or 3 times and you achieve concordant readings, which means within 0.2 cubic centimetres of each other. Note that an outlier is a value which is not concordant. The rough titration value is often an outlier and should not be used in the calculation of the average titers. So in one volumetric analysis, 3 titrations should be carried out. The first should be rough and it would be an overshoot. This will allow you to determine approximately where the end point lies. The second and third titrations should be accurate, within 0.1 cubic centimetres of each other, with dropwise addition until the end point is reached. And a typical table to record results in is shown here. So we've got the rough, first accurate and second accurate. The initial burette reading, the final burette reading, and then the titer is the mean or the average of the two. Indicators then are used. They're substances which change colour depending on the conditions. So when an indicator changes colour during a titration, we say that the end point of the titration has been reached. And an indicator is chosen so that the point at which it changes colour corresponds to the point, in the case of an acid-base titration, at which the solution in the flask has been completely neutralised. So some common indicators and their colour changes are given here. So we have methyl orange, which is red in acid, yellow in alkali, and it's suitable for strong acid, strong base titrations or strong acid, weak base. Phenolphthalein, which is colourless in acid and pink in alkali, is suitable for strong acid, strong base and weak acid, strong base. So you must decide what type of titration is being carried out and choose the appropriate indicator. A weak acid or base is one which partially dissociates in solution. A strong acid or base is one which fully dissociates in solution. And there are pictures here then of the phenolphthalein and the methyl orange. Examples of strong acids include hydrochloric acid, sulfuric acid and nitric acid. Weak acids, ethanoic acid, which is vinegar. Strong bases, sodium hydroxide and potassium hydroxide. And weak bases, ammonia, sodium carbonate and sodium hydrogen carbonate. So we go now to an example of a calculation. 25 cubic centimetres of a solution of barium hydroxide of unknown concentration is placed in a conical flask and titrated with a solution of hydrochloric acid, which has a concentration of 0.06 mol per dm cubed, and the volume of the acid required is 20.43 cubic centimetres. Calculate the concentration of the barium hydroxide solution. The first thing you need is a balanced equation for the reaction, and then in your first calculation you're going to calculate the amount of hydrochloric acid delivered, or which is the solution of known concentration, by using the expression moles is volume times concentration over 1,000. So we know the concentration is 0.06 and the volume is 20.40. Plug those into the equation and we get 1.22 by 10 to the minus 3 moles. Second step is to calculate the amount of barium hydroxide, which is the solution of unknown concentration, which reacts with this amount of hydrochloric acid by substituting in the expression derived from the equation. So if we go back and look at the equation, we have 1 mole of barium hydroxide and 2 moles of hydrochloric acid. So the ratio is 2 to 1. So the amount of barium hydroxide is half the amount of hydrochloric acid. So a half times 1.22 by 10 to the minus 3 is 6.1 by 10 to the minus 4 moles. Next, we calculate the concentration of the barium hydroxide by substituting it into the expression concentration equals N times 1,000 over V. We know N, we know V, we put those in. So 6.10 by 10 to the minus 4 times 1,000 over 25, which gives us 2.44 by 10 to the minus 2 moles per dm cubed. So there are two ways of doing a calculation. Either all of the numbers are kept in the calculator, or the individual steps are presented at each stage. There's also the problem of significant figures, but whatever is done, it must be done correctly. 0.0600 is the concentration of the acid and it has 3 significant figures. 20.40 is the titration value and has 4 significant figures because the last 0 could be a 5. This is why this 0 is kept in the calculation, but it could be omitted. The answer will need to be presented in terms of 3 significant figures because this is a justifiable degree of accuracy. So we see here the calculation again, 0.0600 times 20.40 is 1.224 times 10 to the power of minus 3, which the 3 significant figures is 1.22 by 10 to the minus 3. Dividing that by 2 or multiplying by a half, we get 6.1 by 10 to the minus 4. So if the numbers 0.06 and 20.4 have been left in the calculator and divided by 2, then we would get a slightly different answer, which would be 6.12 by 10 to the minus 4. So back to the calculation. If we put those figures in, the answer 6.12 by 10 to the minus 4 would have given 2.45 by 10 to the minus 2. So the calculation of uncertainty then is important. It's an estimate attached to a measurement which characterises the range of values within which the true value is thought to lie. It's normally expressed as a range of values such as 44.0 plus or minus 0.4. So when glassware is manufactured, there's always a maximum uncertainty or error. It's usually marked on the glassware. Error is the difference between an individual measurement and the true value of the quantity being measured. So the significance of error in a measurement depends upon how large a quantity is being measured, and it's useful to quantify this uncertainty as a percentage uncertainty. Percentage uncertainty is the uncertainty divided by the measurement times 100. And when a burette is used to calculate uncertainty, there are 2 uncertainties associated with it. So if a burette has an error of 0.05 cubic centimetres, in an initial burette reading, it was 0.05. What is the percentage uncertainty then if the final burette reading is 24.55? So the overall uncertainty of any volume measured in a burette always comes from 2 measurements. So the overall uncertainty here is 2 times 0.05, which is 0.01. The tighter value is 24.55. Take away which is 24.50. And then to work out the percentage uncertainty, it's percentage divided by uncertainty times 100, which is 0.4%.